Hello everybody and welcome to another edition of the Physics Corner, a series of videos in which we solve and set up simple physics problems. I'm your host, Dr. Christopher Cirola. In today's episode, we're not concerned so much with solving an individual particular problem, but with the symbols and the quantities that you use when describing problems. So this is an introductory video. This is a video that you perhaps should watch before you watch any of the individual videos talking about specific problems. So, physics is a topic or a discipline that makes use of quantities. What is a quantity? A quantity is a concept that can be expressed with a number. Now that number might be a measurement, it might be a calculation, but in either case, it is a value of something. Even if you don't know what that number is, we still will talk about it in this fashion. Now this is not to say, of course, that physics is superior to other topics necessarily, or that it's better. Of course it is, but that's my opinion. But rather, this is simply how physics acts. So this is the way that we behave in physics. We use quantities to describe most of what we're doing. Now, because we're dealing with numbers so often, it also makes sense for physics, or people in physics, to use math as our basics of language, if you will, for describing how this works. And that means symbols, and symbols being abbreviations for various quantities and other items, which we're going to describe today. So let's go ahead and get started. Now, what are some of the most basic or most common kinds of quantities that you might encounter in physics? For this particular class, Physics 1, we are usually dealing with something called mechanics, which is more or less the physics of everyday life, if you will. Things like motions and distances and displacements, those kinds of ideas. And so we're going to start there. As we go along during the semester, you will find that we'll introduce different quantities and different symbols. But let's go ahead and get a start on this here. And not only is our purpose here to introduce some of these quantities, but also to give you some feedback on how to make use of them. Right? So let's go ahead and get started. One of the most basic kinds of quantities is time. So very simply, how long was the duration, say, of something like a physics class or a physics video? That is a time. And the symbol for time, the abbreviation for time, is usually little letter t, like that. So, as an example, let me go ahead and make a separate column here for that. We could say, for example, t equals, say, 5.0 s. And what does that mean when we write down something like this statement here, this math statement? It says the amount of time that it took to do this particular activity was 5.0 seconds. Now notice the t, the quantity symbol, will always be on the left-hand side. The equals tells you what you're going to describe. We have a number value, and then, if necessary, we have a unit to express the size or the amount of that value. Notice that the unit is also a abbreviation. I could write out the word seconds, but here I've abbreviated it. We have a separate video that talks about the use of units in some detail, so I'm not going to dwell on it much here. I'll simply state that we're also doing that. But notice the way we construct a sentence then. The amount of time equals 5 seconds, like that. Okay. So, what other kinds of symbols or quantities might we have? Well, let me go ahead and put in another one in the same row, capital T. Now, in this particular case, that could stand for a specific kind of time called a period. A period is an amount of time for a process to repeat itself. Now, not all processes, not all situations repeat, of course, but for those that do on a regular basis, it's often very useful to understand what the period is. And so, for example, if you're watching an object swing back and forth on a string, like a simple pendulum, or if you talk about how long it takes for the entire planet Earth to rotate on its axis, those are examples of periods, the amount of time it takes to come back to original starting conditions. Right? Because it's a special kind of time, it's common, especially in introductory physics classes, to use capital T as a symbol. In both cases, whether it's a little t or capital T, they're both kinds of times, if you will, and the units are seconds. The standard units are seconds, like that. Okay, so what else might we encounter in everyday life? In physics, everyday life, that is. How about the symbol x? Now this one requires a little bit of explanation and is worth digging into a little bit because this is not going to be used in the same fashion that you're probably used to using it in, say, a math class. Typically in a math class, x is the independent variable, or it's an unknown quantity, things like that. We have a little bit more specialized use of the letter x in physics. We tend to use the letter x for a special kind of distance. Now, you'll also hear during your classes in physics uses of words like not just distance, but displacement or radial distance, length, width, and height. Things like that, of course, will also come into play quite often. But distance will be our catch-all term for us today, and x is a kind of distance. Now, quite often, not a guarantee, but quite often x represents a horizontal distance. So how far, say, across a page, for example, might you go? As opposed to, say, how far above or below you might travel, or say, something like that. So that's typically what x is used for. That comes in quite handy. So if we were to express x, let's suppose I say x equals, say, 2.68 m. That particular statement would be the distance we traveled, or the position, more specifically, we're at, is the 2.68 meter mark. That'll give you an idea. Again, little m is abbreviated for meters, which is the standard unit for a displacement or a distance idea. Now, not only do we have x, but because there are many different ways to represent distances or variations on that theme, we also have many different symbols. And so, quite often, you will also encounter the little letter y. If you have x and y in the same problem, chances are x represents something like a horizontal distance and y a vertical distance. So, like this, and then say going up above the paper like that. Or if you're sketching it on a piece of paper, you might sketch horizontal this way and vertical up that way if you're trying to sketch what you're doing on a piece of paper. But y and x are separate. They're not representing the same kind of distance, and so different symbols, right? You also might encounter, for example, the letter r. Quite often, that represents the radius of a circle. Or, a little bit more generally in physics, the distance from some central point to a specific location in a straight line. And that's what a radius of a circle is, right? You start at the center of a circle and go to the edge. Well, radial distance is the same kind of idea, just you don't necessarily need to have a circle involved, but it's always a straight line distance. The reason it's different than x or y is because you don't have to go horizontal or vertical. You can go at any particular angle you want, or that's necessary in the problem to get there. One more I'll throw at you, because this comes up quite often in early physics classes like this. I'll throw in the letter h. H is often used specifically for height. Height can be, say, the distance above or below some reference level. So, for example, I've got this pad of paper on a table, and I might say, oh, the height of the table is, say, 0 meters. Then I take my pen and move it upwards a little bit, and that might be, say, 5 centimeters above the paper. And in that case, I could say, oh, h equals 5 cm, or the height above the table is 5 centimeters. Makes sense, I talk about it that way, right? There are many different ways to describe different distances, therefore, again, many different kinds of symbols we might use. Right. But if you're going to encounter one, at least in particular, or one to start with, x is going to be the one that you see most often. Most of the time, if you're taking the lab for this class, and most of you will be, if you're using software to measure things in lab and they talk about a position of an object, chances are on the lab software, you plot that idea, again, x will probably be the symbol that they're using. Okay. All right, what are some other basic or common quantities that you come into play with or come into contact with, say, in physics? Another, I'll say m, for an idea called mass. Now, later on in your course, your professors will have very specific ways to identify or to give you a definition of what mass really stands for. For the moment, and this is not official, mind you, for the moment, you can think of it as something like the amount of quote-unquote stuff that an object possesses. You'll get far more specific and far more careful about your definitions later, but that gives you at least a starting point. It's not the same as weight, by the way. Weight always involves or includes gravity. Mass is a standalone, so how much material an object has is intrinsic to itself. That's separate from whether or not it has gravity acting upon it. So I could be say, an astronaut here on Earth with a mass of 200 kilograms, me and my spacesuit and all that both together. Or I could be, say, floating in space somewhere. I could be on the space station. I could be on the moon. And I have the same mass. But my weight would be different because the gravity effect upon me is different in all those different situations. So just to say it out loud like that, the standard unit of mass is the kilogram in physics. So I could say, for example, I already said it, I might as well go ahead and write that out. Let's suppose that an object's mass is 200 kilograms. And it might look like something like that. Okay. Now, in some situations, you might see where a person might use a capital M, and the only time or distinction that's used is just more for convenience than anything else. That probably means that the mass is very, very large. So, for example, if I was talking about, say, the force of gravity between, say, my pen and the entire planet Earth, I might say the mass of the pen is represented by little m, and a mass of planet Earth is capital M, right? I might do that. But that's a convenient thing, nothing more than that. By the way, notice something that's happened already. We have a little m here, and we have a little m there. This little m stands for mass. That little m stands for meters. How can you tell the difference? You tell the difference by context. Mass is a quantity. So when I ask a question like how much mass there is, that's m equals something. That's a quantity I'm trying to solve or describe. Over here, meters is a unit that's used to express the size, if you will, of a distance. So notice how this works. The number is placed in front of the letter m here to stand for that idea. More specifically, x equals 2.68 m. That tells you that it's a distance equals this many meters. So it's all in context, right? We try our best not to mix and match letters, but that will sometimes happen, that you might encounter some of these letters in several places in the same problem. This is part of your task, is going to be to memorize and to learn each of these symbols, where they're placed, what they're used for, what context you're using them under in order to keep them straight. But that's a fair warning for that. Okay. So these are some sample quantities that are pretty basic. I'm not going to go through all the possible physics quantities. That would take us a few days, to be quite honest. And it's not necessary for here. Again, this is just an introduction to get us started thinking about these ideas. But that's an example there. What about a quantity or a symbol that is something that's a compound? So each of these particular quantities here is a standalone. So time cannot be broken apart into something more basic. There are no parts of time, for example. There are no parts to distance. There's no parts or pieces of mass. You can't break a mass into something, into several different bits. That's not a thing. But we could say, for example, talk about an idea like speed or velocity. So let me write down the name of the quantity here. And in physics, we typically use a little letter v to stand for that idea. So speed or velocity is how fast you're going. Now, we'll talk a little bit later in this video what the difference between these two quantities is. I will say at the moment that velocity is a little bit more important, or incorporates a little bit more information, it's probably a better way to say it, than speed does. And so it's v that gets the letter abbreviation rather than s. And by the way, physics, if we use the letter s at all, we have a completely different thing for that. So I might say, oh, the speed that we're driving down the road is 10 meters per second. For example, I might say something like that. Right. Give you another one, one more just to kind of round out some of the very simple introductory quantities that you can encounter in your first few weeks of the class. Let's throw in the little letter a. That stands for a quantity, more often than not, called acceleration. Acceleration is a rate of change of velocity. How fast are you, say, speeding up or slowing down or turning, those kinds of things. That's an acceleration idea, and that's a rate of change of a rate of change, if you will. So it's a little more complicated. Notice that velocity, meters per second, and acceleration, which will come in, say, let me write down a sample number, just to have a number in front of us, say 3.5 meters per second squared. Notice that that comes in compound sets of units as well, which is to say, these quantities here, time, distance, mass, those are fundamental. They can't be broken down into simpler things. Velocities and accelerations can. A velocity consists of a combination of a distance and a time. Acceleration consists of a combination of distance and time, or even velocity and time, if you want to define it that way. And at some point, of course, during this class, you will do exactly that. Here's the major point, though. We have these symbols here that stand for various different kinds of quantities here, so it's shorthand. And we can write equations to express their values in these kinds of ways. These symbols are shorthand, they're abbreviations. Why do we do this? For starters, it's a lot more succinct. It's a lot more clear to write it this way. Instead of writing out the word acceleration all the time, I can just write little letter A and I'm done. But also, in the long run, it's easier. Once you get used to using the symbols, it's a lot easier to write equations and to write calculations and measurements using the quantity symbols rather than always writing the quantity name out in full. So it's a lot easier for us to do it that way, and that's why we're doing it. Okay. All right. I do want to talk about a couple of special cases of symbols that are used either for quantities or other ideas. And so let's do that quickly. So, I mentioned there's a difference between speed and velocity before. So, what is that difference? Speed is what we call a scalar quantity, and velocity is a vector quantity. By the way, it's just coincidence that the words scalar and vector also start with S and V. That otherwise has nothing to do with anything. But speed is a scalar quantity, which means what? A scalar quantity is just an amount of something. Or you might also hear sometimes your physics professors talk about the magnitude of a particular quantity. That's a scalar. It's just an amount. It's just a number. Now, you can have positive and negative quantities, you'll find out, or positive and negative scalar quantities. Here's an example of something that would work. Suppose that you are going to get lunch and you need to, say, hand over $10 to buy lunch. That is a negative $10, right? You are paying $10 to get your lunch. So it's possible to describe, say, a scalar in terms of negative or positive number. That's okay. Sometimes you do, sometimes you don't. But in either case, that's perfectly fine. Velocity, in other words, is a vector quantity, and vectors are both amounts and directions. And by directions, I mean indicating where are you specifically going. So, if I'm driving down the road at, say, let's bring back our 10 meters per second. This statement tells me that this is a speed. How do I know this is a speed? Because I'm just describing an amount. If I were to say this, now I've described a vector because I've identified both the amount and the particular direction in which we're traveling. Notice something else I've added to this. I put a little arrow on top of that. The little arrow that we have indicates a direction or indicates a vector quantity. If you don't have an arrow, there's no need for an arrow, then it's just a scalar. So all numbers, pure numbers, are scalars, right? The number 5 is a scalar, number 10 is a scalar. They don't have any directions attached to them, just to have a number. But the moment I talk about, say, I take my pen and I drop it and it falls down at a certain rate, suppose I say, my pen accelerates downwards with a rate of 10 meters per second squared, I have now described a vector, and if I want to write that carefully down on paper, use an arrowhead. Now, just to say this, in typical textbooks, they don't tend to use the arrows. In textbooks, they use boldface for vectors. So, you would see something like this in a textbook. Now, you don't see that written by your professors on the board or me on the paper here for the very simple reason, that's a pain. That is very difficult to write things like that as they're going along. It's a lot easier and just as clear to put a little arrowhead on top of it to represent that. But if I do that, or if your instructors do that, That's what's going on. The arrowhead represents a vector. Lack of an arrowhead is a scalar. If you're looking in a textbook and it uses boldface, that's a vector typically. If it uses regular print or regular font, that is a scalar. Two more items I want to talk about before we leave off today. Let's suppose we have something that looks like this. And I'll just go ahead and write that down like that. There's a little bar above this. What's that stand for? This little bar here in physics indicates an average result. Now, that is a discussion for a different video or a discussion that your professors will have with you as to what averages are in physics. I will say here that averages in physics are usually time-based averages. They're not simply adding up some numbers and dividing by the total number of data points. It's a little bit different. But for the moment, I'll simply say that if you do see a bar written above a quantity, it usually means average. So I could, for example, talk about the average speed at which I traveled on my trip, say, from my house to my office. Right? So I got in the car and I drove and I had an average speed of, say, 10 meters per second, which, by the way, is about 22 miles per hour, give or take a little bit. Now, that doesn't mean that during the entire trip, my speed was always 10 meters per second, right? That's not what we're saying. We're saying over the entire trip, the average speed was 10 meters per second. That's what the bar indicates. One more symbol I want to introduce here as usage is this fellow here. Let me make it a little bit bigger. This is called the delta symbol. And the delta symbol has a very special meaning in physics for us. It means the final number subtract or minus the original number, or if you prefer, initial number. Always done in this order, final minus original, always like that. It doesn't matter, by the way, if you start off with a small number and end up with a big number, or you started with a big number and end up with a small number, it makes no difference. It's always in that order, time order, specifically final minus initial. When I say then something like this, what does that mean? This means a change in distance. So x was a symbol we used earlier to stand for a distance, right? The delta, or the triangle symbol in front of it, means a change in distance, which means you could say it was the final position minus the original position. This, by the way, gives us to our very last comment. Notice I introduced subscripts right here and here. What are subscripts all about? Subscripts are used to identify a specific item, a specific value of a quantity within the more general idea. And so, for example, this is the final position. This is the original position, like that. So they're both positions. X always represents a position or a distance that you're at, right? But if I put a subscript on it, then I can distinguish between two or others, more, different versions of that same quantity. And you will find out as you go along in physics in your studies that this change of something, whether it's a change in distance or a change of velocity, a change of force, a change of energy, whatever, that quite often in physics, it's not the absolute number or value of a number that's really the important thing. It's usually the change. And so this delta symbol is very useful for us. It represents something that has a lot of meaning. So you're going to see a lot of that as you go along in your career here in physics with us. All right, everybody, that wraps it up for this episode. Technical assistance comes from Sydney Gautraw and Sophia Turner. Funding for this project is from the University of Mississippi and the University of Southern Mississippi. We film these videos in Hattiesburg, Mississippi proper. I'm your host, Dr. Christopher Cirola. Thank you for your attention, everybody, and clear skies.